Welcome, everybody. So it's our great honor to invite Professor Richard James from University of Minnesota. He's my advisor, and he's beyond my advisor. Not only teach me the academic and how to do the research, besides he also teach me the philosophy, how to face different problems at different stages. So here is some brief introduction of Professor James. He's McKnight University professor. He was Penrose professor for 10 years at University of Minnesota. As far as I know, he won a lot of prizes. As far as I remember, the most recent one is von Karman Prize, awarded by Siam. Also, William Prague Medal from Society of Engineering and Science. And his topic today is theory-based discovery of highly reversible phase-transforming material. And as I can see here, there are many bridges. Actually, he's building bridges between mathematics and mechanics, also building bridges from science to engineering. So let's welcome Professor James.
Very good. So thank you, Sherry. It's a great pleasure to be introduced by such a successful former student and her successful husband who's sitting next to her, who's also a former student of mine. So it gives me great pleasure to speak about this topic and a great pleasure to visit HKUST. And in fact, Sherry Chen and Yintao Song made a lot of contributions to what I'll say, and you'll be able to see that through the various references in the talk. So you can say that Sherry Chen really changed this field a lot. So it's about the reversibility of phase transformations, and so I start with a very simple. This is a very basic talk. So in fact, you can interrupt me if you want. And I start with a case of a highly non-reversible phase transformation. That's the alpha-beta transformation in tin, the element tin. So if you cool tin to about minus 15 C, and you just wait a bit, you'll see that. And that phase transformation is so destructive that it completely pulverizes the piece of material, and of course it's highly non-reversible. So of course, why is that not reversible? You can read in textbooks about that, and they'll tell you that it's because of the volume change. It has such a big volume change that the material can't support this volume change and it breaks apart. So we'll return to that explanation in a little while. The phase transforming material actually that's most used in technology, actually it's very prominent in Minneapolis, where I came from. I come from the University of Minnesota. This is designed to make Sherry Chen nostalgic about her graduate studies and Yintao Song. And there's her former department. It's a center, that city that I come from is a center for medical devices. And this is the most used material in those medical devices, slightly nickel-rich, nickel-titanium alloy. And in these graphs, you can see measures of the reversibility of the phase transformation. So this is calorimetry, heat flow versus temperature. And you can see that this material transforms at a different temperature on heating than it does on cooling. And in fact, this is calorimetry, so the area under here is representative of the latent heat of phase transformation, which is released on heating and absorbed on cooling. So the fact that there are two different temperatures, really transformation temperatures, is an indication of non-reversibility, and in fact, there's even a stronger indication here, is that if you keep cycling, these transformation temperatures actually migrate with the cycles. In that material, and in many phase-transforming materials, it's kind of a generic feature of phase-transforming materials, you can also induce the phase transformation by being up here at the high temperature and applying stress. and in this case you stress induce the phase transformation. That plays an important role in those medical devices, in fact. And you can see that there's another measure of reversibility here. There's also a hysteresis loop, and also with cycling there's a change in the nature of the hysteresis loop, and also a migration of the residual strain. So these are all different ways of measuring the reversibility of phase transformations. The area in that loop is a measure of the dissipated energy. Of course, you do work on the material when you stress it and it undergoes a strain, and the area in that loop is representative of the dissipated energy, which is also changing. So these are all connected with the reversibility of phase transformations. So I'll start by discussing hysteresis. So that's, as I just mentioned, here's another representation. We're going to be talking about phase transformations in crystalline solids, and very often, not in the case of tin, but in another classic case, the high temperature phase is cubic, and the low temperature phase is tetragonal. And by symmetry, so this cube undergoes a distortion by elongating along each of the 100 directions near this transformation temperature to theta C. Of course, there's theta is the temperature here, and of course there's hysteresis in this phase transformation. But by symmetry, that it transforms to one of three forms, and these are called the variants of the low temperature phase. This is often called the Martensitic phase transformation. These would then be the variants of Martensite. And you can have hysteresis is everywhere. So hysteresis, you can by stress, you can pass from this one to this one, back and forth. And this was a particular kind of experiment that did that. And you've got a nice square hysteresis loop in this case. You can also pass from the high temperature phase to the low temperature phase. And you also see hysteresis here. But one of the characteristics of this hysteresis that's actually represented nicely in this graph is this graph, the transformation was done at different rates, varying from 10 to 1,000 seconds. That's the period of the cyclic loading. And you can see the loop is almost the same. So that's a characteristic of hysteresis and phase transformations. It doesn't disappear when you go slower and slower around the hysteresis loop. Okay? So that throws out many explanations for hysteresis. And that's true also over here. If you go slower and slower around the hysteresis loop, there'll be a limiting loop, non-zero loop, which is rate independent, and that's called rate independent hysteresis. So you know from that the explanation for hysteresis can't be some kind of viscosity or viscoelasticity, because they would go to zero when the rate goes to zero. So it has to be some other kind of explanation. I want to talk about that. In fact, these are the conventional explanations for hysteresis in phase transformations. This one was a bit borrowed from magnetism, and that is one explanation is the pinning of interfaces. When you have a phase transformation, you have an interface between the two phases. It meets a defect as it's transforming, and it requires an additional, say, lowering of the temperature or a lowering of the free energy of the new phase in order to cause this interface to pass through the defect. That happens both ways through the phase transformation, and this is related to hysteresis. That's one idea. Another very popular idea and important idea in general in science is thermal activation. And I'll explain that a bit like a mathematician would, and that's, I'm going to write the potential energy of the full atomic system of the material. So of course, so there's 6.02 times 10 to the 23 axes down here, which is a bit difficult to draw, but you can think of it schematically. And people think this potential energy surface is very wiggly, and it's thought to have very steep minima corresponding to the Martensite phase, the low temperature phase, like those three tetragonal variants I was showing earlier. So what is the state of the system? The state of the system is a dot, like that little red dot there. And just like my pointer, that red dot is not stationary because we're at finite temperature. And the motion of that red dot is governed by the equations of molecular dynamics. That is exactly what governs the motion of that dot. And if you raise the temperature, increase the average kinetic energy of motion, this little dot can come out of that little well and go over here, and that corresponds to the phase transformation. And in fact, in the austenite phase, the average position of that dot, so the average position of my pointer, may not even be at a local minimum of the energy. That's called entropically stabilized austenite. But that's the way it is. But you can imagine that it can be somehow much easier when you're raising the temperature to get this dot to come out of this well than it is when you're lowering the temperature for this dot to find its way back into the well. That's thermal activation. Okay, that's a way of explaining thermal activation. And so that would give rise to hysteresis. There's this difference in heating and cooling. Okay. By the way, neither explanation is the most important thing about hysteresis. I'll tell you a third explanation that's sort of one of the main purposes of my talk. So to do that, we have two important people here. And they discovered an interesting algorithm which is useful for determining this matrix called the transformation stretch matrix. So this is a basic quantity. It's a matrix, a 3x3 matrix, which is used to quantify phase transformations. And it's the linear transformation which takes the high temperature phase to the low temperature phase. And now I do a little different example from the cubic to tetragonal one, but I'm going a cubic to orthorhombic example. That's the case where the cube, the transformation consists of the cube. It shortens along this axis, as you can see. And the top face turns instead of being a square, it turns into a rhombus. Instead of being a square, it turns into a rhombus. Looks like that. And it has 3 lattice parameters. And if you use that notation, then the linear transformation written in the cubic basis has this matrix. So that's the transformation stretch matrix or transformation matrix. It has eigenvalues. In fact, the way I wrote it, alpha, beta, and gamma are its eigenvalues. But in this talk, we'll talk about those eigenvalues. We're going to order the eigenvalues. So I'm going to rename them lambda 1, lambda 2, and lambda 3. They're the eigenvalues of this transformation stretch matrix. Now, this is very simple. And in particular, lambda 2 is going to play an important role in this talk. And not all lattices are so simple. And in fact, you can have complex lattices. Complex lattices, it's many materials, many crystalline materials. They consist of a Bravais lattice, all the same, but with different base points. So it's illustrated here. I got 3 base points, a red and a blue and a green one, and there are 3 Bravais lattices. And each Bravais lattice undergoes the same linear transformation. If it didn't, you would destroy periodicity. And it's that linear transformation for complex lattices that we call the transformation stretch matrix. Okay? So that's a little definition. Now, there's actually not just one transformation stretch matrix. There's actually a number of them because, of course, there is symmetry. And you can already see it in the cubic to tetragonal case. So there's the cubic austenite phase in a B2 structure. That's one example. And you can, as I said, one possibility is this cubic to tetragonal phase transformation. You shorten on this vertical axis, and the top face is a square, and it turns into a rhombus. But of course, by symmetry, why turn into a rhombus like that? You could also, instead of pulling the 2 points in the cube like this, you can pull them like this. And that's a second variant of Martensite, and that has this transformation stretch matrix. And of course, instead of the top face turning into a rhombus, it could be this face that turns into the rhombus. And then, of course, there's 2 ways to do that. And of course, et cetera. You can see that there are 6 variants of Martensite in this case. And those are the transformation stretch matrices that go with them. Now, when we do this is a non-heavy lecture of theoretical stuff. So, I'm not going to tell you all the details about the energy we write. But the energies we write, essentially, they have many energy wells, like that picture I drew earlier. They're also parameterized by temperature, macroscopic type theory, and these matrices define the energy wells, okay? There's also some rotational invariance too, that if I take this structure, say this structure, and I rigidly rotate it, of course it can't change the energy. So that's also builds into the energy. And so I'm not telling the details of all that, but I hope you can understand that really what I'm saying is coming from energy minimization or calculation of energy barriers. So, okay, so in this case, there's 6 variants of Martensite. Okay, so now, when we have a phase transformation in a martensitic material, but it actually applies to a great many materials more or less that have reversible phase transformations. Not like the tin I showed you, but many other cases, and certainly, nearly all, you'll see some different examples later, but nearly all reversible phase transformations, if you look at the finest level and you look at the interface between austenite and martensite, you will see this. And this is the great simplifying feature of phase transformations, is this particular structure. The fact that this structure is quite relevant to many properties, transformation properties. Okay, so how do we understand this structure? Okay, so there's the austenite phase, say that's a cubic phase. This material undergoes, it's a copper aluminum nickel alloy. I didn't write that, but it is. And at a particular composition that has this phase transformation. Professor QP Sun knows this alloy very well. Okay, so what is it? Okay, there's the austenite cubic phase. By the way, this interface is very beautifully straight. And in the early days of martensite, people measured the normal to this interface. And then they expressed the normal in components of the cubic basis. Take the cubic basis, write the components of the normal in that basis. And they were not small integers. So that may not seem so significant to you, but people were extremely puzzled by this, because if in a material you see such a beautifully flat interface, and in a crystalline structure, you would expect it should be a so-called rational interface. It should have, its components in the cubic basis should be small integers. And they were not small integers. So somehow, this interface is not governed by crystallography. Okay? It's only partly governed by crystallography. It's governed by other things that I'm about to tell you. So here's how it goes. This is, in fact, 2 variants of martensite over here. So why is it 2 variants rather than just 1 variant? If you put 1 variant here, you would find, and you allowed this interbase to be free, you would find that you would be forced to put a transition layer between that single variant and the austenite, and there would be a huge amount of energy in that transition layer. And no matter how you made this transition layer, no matter how you made this interface, it would contain a huge amount of energy. Okay, so it's highly energetically unfavorable to have a single martensite variant over here. But if you have 2 of them, and you layer them like this, and you make them finer and finer, there's in fact a stressed, elastically stressed transition layer here in this material. And in fact, you can show that if you make them exactly the right volume fraction, you can see the volume fraction is quite uniform here. It's even more uniform than it looks if you measure it. And you can show that if the volume fraction is just right, and this interface is just right, it's the normal to this interface is just right, you can drive the elastic energy in this transition layer to 0 by making these bands finer and finer. Okay? That's the essence of something called the crystallographic theory of martensite that I'll talk about later. So that's great, and in fact, that idea explains the normal to this interface and explains the volume fraction, and it's a very successful theory in phase transformations, is the crystallographic theory of martensite. What it doesn't explain is, according to the crystallographic theory, you should make these finer and finer and finer to drive the elastic energy in this transition layer to 0. And of course, they can't be infinitely fine in a real material. So there's some fineness here that's quite uniform, and it also gets a bit finer toward the interface. That's also an interesting aspect of it. And the point is the following. If you make it finer and finer and finer, you'll drive the elastic energy in this transition layer to 0. But there's a tiny interfacial energy on the boundaries of these bands. And of course, if you make them finer and finer and finer, the interfacial energy goes to infinity. So what you see in this picture is a compromise. It's a compromise between the interfacial energy on the bands and the elastic energy in the transition layer. But in fact, to predict the normal to this interface and the volume fraction, you only need to think about the elastic energy, but that's the way it is. Anyway, the upshot is this picture contains two sources of energy. It contains an elastic energy in this transition layer. It contains interfacial energy, small interfacial energy on these bands. And they're kind of matched. Okay. If you think about it, that suggests a possible reason for hysteresis. And it goes like this: if you imagine you're totally in the austenite phase, you're all cubic, and you're cooling the material. You get to a point where a single variant of martensite, without any interface and so forth, has less energy. Okay, so the energy well of martensite is lower. And you would say, okay, so why don't you start forming these kind of, in fact, they look a bit like this. You start forming these little nuclei, twinned nuclei of the martensite phase. But as soon as you form them, you're forced to take these two positive sources of energy. So if you want to really transform them, you have to lower the temperature more in order to have a free energy decreasing path to the new phase. Okay, so that's a kind of energy barrier explanation for hysteresis. Transformation is delayed because the additional bulk and interfacial energy that must be present merely because of the coexistence of the two phases has to be overcome by a further lowering of the energy well of the stable phase. Great. And you could study this theoretically, but of course there's a very simple experimental thing you can do, and it's based on this lemma. Remember the transformation stretch matrix and its eigenvalues. So the middle eigenvalue of this matrix being 1 is necessary and sufficient that there's a rotation matrix such that this algebraic condition is satisfied. A tensor n is just the matrix with components ai and j, the ijth component. So that's the compatibility condition between a single variant of martensite and the austenite. The austenite is the identity in this notation. So if you satisfy lambda 2 equals 1, the middle eigenvalue of this matrix equals 1, you don't need the elastic transition layer. And you don't need the interfacial energy on the bands, because there are no bands. You don't need the bands. You can, by energy minimization, this is the natural interface between austenite and martensite. Of course, there could be a tiny interfacial energy on this interface, but there's only one interface compared to all these bands and so forth, no elastic energy. And in fact, this lemma tells you, in fact, there are two such interfaces, and they look like this in a particular kind of realistic case. So if you really believe this story, you should somehow make the middle eigenvalue of this matrix equal 1. So how do you do that? It turns out that the composition of the material, if you start changing the composition of the material, you change these numbers, alpha, beta, and gamma. You change these eigenvalues. So you can think about adjusting the composition of your alloy to make lambda 2 equals 1. So that's the idea. And then this interface should not become banded. You should end up with this, and so forth and so on. Then you should lower the hysteresis. So we had that idea, and then we tried it experimentally on some bulk samples. And then we were very fortunate to have some collaborations with people who do combinatorial synthesis, which has turned out to be a great tool in this. And I'll show you a compilation of lots of data. Here's on nickel-titanium alloys, nickel-titanium, copper, palladium, gold, platinum, and it's not even the full set, but this is very typical kind of data. And you can see, and each marker is a different alloy. And there's the width of the hysteresis loop versus, of course, you could plot the width of the hysteresis loop versus some compositional variable here, and these dots would be all over the place, but you replot the data as hysteresis versus lambda 2, and you see this very sharp drop. Okay. So that's really surprising, and in particular, there's some alloys here which seem to have near zero hysteresis, and that's there's some record-setting alloys. I'll show you the world's record in big first-order phase transformations a bit later, but this is quite striking data that neither thermal activation nor the pinning of interfaces may be the most important thing, but the energy barrier set up by the austenite-martensite interface. Now I want to do something, come back to tin. So as I said, everybody would say that it's the volume change in tin that matters, and that's why it falls apart and so forth and it's kind of infinite hysteresis or whatever. So I'm going to take this data, actually a part of this data, and you should really divide all these numbers by 2. So this should really move down by a factor of 2 because of the way the hysteresis was calculated in these numbers. But anyway, just it's not important. So I've replotted a part of this data, but not the hysteresis not versus the Biddle eigenvalue, but versus the determinant of the transformation stretch matrix. That's the volume ratio of the two phases. So when that determinant is 1, the two phases have the same density. Okay. So, and you can see that some of the alloys with the lowest hysteresis and some of the alloys with the highest hysteresis have no volume change. So volume change doesn't correlate at all with the hysteresis. Lambda 2 correlates with the hysteresis. Okay. Okay. So this is a graph. This striking graph. When it was measured was we measured first some of these bulk alloys, and as I say, there were these combinatorial measurements, and people asked, why didn't people see this before? Because people made many thousands of nickel titanium alloys since the 1950s, and so why didn't they see this drop? It's because it's extremely sensitive to composition. So when people made their alloy series before this, they always jumped across this lambda 2 equals 1 point. And you can see that in this graph. So we took the nickel titanium palladium system, and this is bulk measurement. So this is not films, this is bulk. And you can see we changed composition. So you can see it's quite sensitive to composition. And in fact, we used to think that PD11, so nickel, we're substituting palladium for nickel, so 11% palladium. We used to think that was the kind of lambda 2 equals 1 alloy and had hysteresis around 16 degrees. Then we went in this little box, and this is work of Vijay Srivastava. He changed composition by 1/4% increments. Okay, so very small compositional changes. And he got that down to 2 degrees. So each dot is a different alloy. This is 2 different alloy series. In fact, this one was down to 3 degrees. That's really very small hysteresis for something like this. So that shows incredible compositional sensitivity. And if you really want to get your lambda 2 equals 1 alloy, you should go 1/4% compositional changes. Now, if you go 1/8% compositional changes, I have no idea if you can get, maybe it can go even lower, I have no idea. But it is very sensitive to composition. There's a nice high-resolution TEM, transmission electron micrograph, of the interfaces. This is, as I say, the alloy we used to think was the lambda 2 equals 1 alloy. Apparently it's close enough that we saw lots and lots of those interfaces. There's the interface between the austenite phase, which is up here. That's the cubic phase. And one of the variants of martensite. You can see it's nearly atomically sharp. These guys, Nick Shrivers and his student Remy Delville, they measured the normal to this interface because this TEM lines up the columns of atoms to be 7 minus 5, 5. Turns out 7 minus 5, 5 is that n, very closely. And the angle of rotation is the angle of rotation, this rotation matrix Q. So there's a nice agreement between what you see in TEM and the calculation. So those are all nickel titanium alloys. You could say, well, what about, what does it work on other materials? This is nickel manganese indium and nickel manganese tin. And sure enough, this was tuned down to about 4 degrees. This is hysteresis versus composition, replotted versus lambda 2, the middle eigenvalue. And you can see, again, there's a very sharp drop. This got down to 4 degrees. I believe with tiny compositional changes, you could make this 2 degrees hysteresis. So that's a magnetic material, so it's even dominating the behavior of magnetic materials. It's this elastic part which is the most important in the hysteresis. Okay, so that's hysteresis, and once you see that, you can think, well, maybe there are stronger conditions of that would be called the condition of compatibility. And you can imagine there could be stronger conditions of compatibility that you could try to achieve. And to do that, I need to tell you a little bit more about the crystallographic theory of martensite. So, as I said, there were some bands here. There's some elastic transition layer. There's the austenite phase over here. And first, the bands. Okay, so the bands, I've written them and enlarged a bit the deformation. And we picked 2 variants of martensite, Ui and Uj. And we solved the compatibility condition between 2 variants of martensite. That means we consider a deformation which takes a homogeneous cubic phase into something which looks a bit like that. Don't worry about the mathematics if it's not familiar, but that's enforces compatibility, and the linear transformation which works in here is Ui and works in here there is Uj, and this R is there to allow rigid body rotation, which is needed to make them compatible. And then the condition, again, it's don't worry about the details, but the condition under which you can drive the elastic energy to 0 on this interface is again a compatibility condition. It's a compatibility condition like this. It's essentially that the average deformation of this is compatible with this, and that's this condition. Again, don't worry about the details, but I'll show you a little bit of the algebra. This, for the mathematicians in the audience, these conditions would be sufficient that you could write a minimizing sequence which looks like this and drives the elastic energy to 0. That would be the mathematical interpretation. So you have to let's imagine we solve this. This is known to be easy to solve. You can find explicitly the R, the A, and the N. Of course, these 2 are given. And there's 2 solutions, in fact, and usually they are interpreted as type 1 twins or type 2 twins. These are called twins for kind of obvious reasons. And so let's imagine this has been done, and so it is easy to do. Now we're trying to satisfy this, and this rotation matrix is free. F is the volume fraction of the 2 variants of I versus J, and we have to solve this. And the way you solve this, if you've taken the right courses, is you take this transpose times itself to get rid of this rotation matrix, because it's hard to solve for that, and you get this condition. And now, the reason I do it this way is because the only unknown on the left-hand side here is F, just a scalar. And so to satisfy this condition, it turns out it's, again, I just used that lemma, it's just that the middle eigenvalue of this matrix has to be 1. So, but now I get to adjust the F. Okay, so suppose you have a matrix. It depends on the volume fraction F. There's the matrix. And you want to figure out if its middle eigenvalue is 1. Well, you would subtract the identity and take the determinant, right? That makes sure that at least one of the eigenvalues is 1. Now you have to worry about whether it's the middle one. But okay, we start this way. Now, this is, G sub F is here. That's quadratic in F. And when you do determinant, that's cubic. So it looks like a 6th order polynomial in F. But because of the special structure, it's actually quadratic, and it's also symmetric about a half. F is a volume fraction going from 0 to 1. So it looks like that. So it's a quadratic. So the next two slides are about quadratic functions, which are symmetric about 1/2. So they look like that. If you plot that, now remember, G sub f depends only on the lattice perimeters of the two phases, right? So it's all geometry. So I take some martensitic materials and I just calculate this and what kind of graph I get. Well, if I take a steel, many martensitic steels, this is the way it'll look. It has no roots, so there are no solutions of the crystallographic theory of martensite. So actually, some steels do have roots, but that's the way it is. So that's already quite useful thing to know. Now, this material, for example, it's not like that. This material looks like that. So this material, the quadratic function, its value at 1/2 is different from its value at 0. And therefore, it has two roots. It's symmetric about 1/2. So it has two roots, f star and 1 minus f star. And then once you know that, you have to worry about that a little inequality that tells you the eigenvalue you got is the middle one. And then you find the solutions. In fact, for f star, there are two solutions. And for 1 minus f star, there are two solutions. You take one of those solutions. I forget which one it is. You compare with this picture, volume fraction, normal to the interface, so forth. You agree very nicely with that picture. Okay. Now, we've been talking about lambda 2 equals 1 material. Suppose we have a lambda 2 equals 1 material. That's a material in which the transformation stretch matrix has middle eigenvalue 1. That's the case where at volume fraction 0 or volume fraction 1, we have a root. So, of course, the solutions look like that. I've discussed that case, and that corresponds to low hysteresis. Okay, now, what's the interest? What's the most, if you were trying to make the most degenerate material possible, what would you do? You have a quadratic function. It's symmetric about 1/2. You could make it identically 0, okay? Why not? So you could make your quadratic function like that, and that would have every volume fraction would be a solution, correspond to a solution of the crystallographic theory of martensite. Okay, that we call the cofactor conditions, and we refer to those kind of conditions as conditions of supercompatibility because it really has a dramatic effect on the way the two phases can coexist. So you have a quadratic function which is symmetric about 1/2. How do you make it identically 0? It's very easy. You make sure that the endpoints are 0. That's lambda 2 equals 1. And you make sure the slope is 0 at 0. That's this condition. And then, of course, you have to worry about whether the eigenvalues you found are with the middle ones, and there's some inequality, and it's that inequality. Those are the cofactor conditions. Okay, so what do they mean? They mean this. They mean that you can continuously vary the volume fraction from 0 to 1 of two martensite variants. So we have now, imagine we have a material that satisfies those conditions. And at each, and I really exaggerated the strains here, so there's huge exaggeration of the strains, but you can see there's low energy interfaces all the way from 0 to 1. And you might think that that's because maybe there's some accident here where, as I change the volume fraction, this laminate doesn't actually deform. Then you could imagine this could be true. But in fact, it's deforming a lot. So I tried to draw, and my color coding is not very good, but this is the strain ellipsoids for the endpoints. And you can see that there's a lot of straining going on when you pass through these pictures. And it's nevertheless the material is compatible with the austenite. This is more detail about different kinds of, this depends on which twin system you choose. There's a story about if you satisfy one twin system, which other ones is it satisfied for. It turns out that this is the way it looks. It's a plane strain in the case of compound twins. And for type 2 twins, it turns out that the twin boundary is parallel to the austenite-martensite interface. That's kind of interesting because you don't need any transition layers in this case. So there's no elasticity in this. These are zero elastic energy structures. This is one, in fact, this is an important result from Sherry Chen's thesis, is this is a case for half the solutions for the so-called type 1 twins. Again, you don't need the transition layer. So every little region has a change of shape. It can be even, in fact, a large change of shape. Everything fits together perfectly. There's no elastic energy. And in fact, once you have that, you realize you can make curved interfaces. There's all kinds of structures you can make which fit together perfectly and have no elastic energy. It's like a jigsaw puzzle. If you have a usual jigsaw puzzle and you imagine the pieces spontaneously undergo a change of shape, then usually the puzzle would buckle out of plane. But if the changes of shape were just right, it would remain perfectly compatible and stress-free. That's exactly what happens under the cofactor conditions. And these, again, are configurations that Sherry Chen found is nucleation configurations. Again, this is all austenite nucleation at a corner of a martensite. Again, no elastic energy in these pictures. This is a band of martensite in another variant, a green variant of martensite, and this is nucleation of austenite. Again, no elastic energy in any of these pictures. And here's a more complex arrangement with 4 variants of martensite. Every little domain is having a big shape change. Everything is fitting together perfectly. No stress. Okay? So you can see there become many possibilities for how the two phases can fit together under the cofactor conditions. So the great news is, well, Sherry Chen and Yintao Song did it first, and their collaborators in my lab, they systematically changed the composition of an alloy, and they arrived finally at this alloy such that to satisfy these cofactor conditions. So they didn't do that by doing mechanical experiments. They did that by measuring the lattice parameters of the two phases, checking those conditions I said earlier, systematically changing composition to reach that point. That's a story in itself, but I think you can imagine how that would be done. And secondly is a quite interesting alloy from Eckhard Quant's group in Kiel, Germany. I'll tell you about both these alloys. And there's actually a recent example. We knew that VO2 was an excellent starting point. It seems that this work of Miyazaki, Kei Miyazaki, achieved the cofactor conditions in this, but this remains a bit to be seen. So it would be an interesting case for various reasons. Okay, so let's talk about zinc, gold, copper. In fact, it satisfies the cofactor conditions for many twin systems. So, whichever choice of bands you choose, there are many choices of these bands, and it satisfies them in a lot of cases. So that's quite interesting in itself. And this is a graph calorimetry, like I was showing earlier, of various zinc, gold, copper alloys, and it's this one that satisfies accurately the cofactor conditions. And in this particular measurement, the hysteresis is actually 0.2 C. So for a big first-order phase transformation, that's really small hysteresis, amazingly small. It's the smallest I've seen. By the way, if you keep cycling this, it may go up to 1 degree or even 1.5 degrees. It can be even 2 degrees, but this is also a quite typical measurement. Okay, so I was going to tell you something before I show you the movie. Okay, so usually a standard thing about phase transformations is you cycle, you polish a surface, you look at the surface, and you cycle through the phase transformation. You see the phases come and go. It's very typical to see the same, this is generic observation in martensite, to see the same microstructure again and again, formed in exactly the same way. Reproducibility of the path. It's even something called return point memory, which is connected with this reproducibility. That's the generic observation in martensite. So now I'm going to show you what happens if you heat and cool. This is within a polycrystal, but you're going to be looking at a single grain, single crystal. And heat and cool this zinc, gold, copper alloy that satisfies these cofactor conditions. So there's the austenite, there's the martensite. You can see many features in this graph which are very unusual for martensitic phase transformations, like these curved interfaces. and structures, quite unusual structures. And we studied a lot the nature of these structures and, of course, verifying the cofactor conditions and so forth. But it gives you a nice picture of what happens if you really satisfy very strong conditions of compatibility between the phases. It's my longtime collaborator, John Ball, he noticed that the way this microstructure looks, it's like the microstructure was already there and you're revealing it by pulling the rug away from the microstructure. And that itself leads to interesting ways of thinking about this microstructure. Okay, I'll go on if I can. Okay, here's another example. This is a pillar experiment. Again, Sherry Chen was doing this experiment with Zhao Ni at Julia Greer's lab. Oh, there she is. Okay, Julia Greer's lab. You can see the top is going down. In these type of pillar experiments on transforming materials, very often you would get a very distinct, see now it's going up, shear band in this material, and it would have sharp corners and so forth. This deforms nearly homogeneously. So that's very unusual for transforming materials at micron scale. So this material, we interpret that by thinking that in this material you pay so little for the interfaces, and there's so little elasticity that even at micron scale it can be full of microstructure. Some of the ideas about what that microstructure might be are shown here based on the microstructures possible with the cofactor conditions. But this pillar can be cycled 100,000 times at quite demanding conditions. It's in compression, but it's 300 megapascals, sort of peak stress of 5, maybe 600 megapascals, and very narrow stress hysteresis, and also 6 to 7% strain. Those are quite demanding conditions. So it's really quite hopeful for maybe not this particular alloy, but satisfying these conditions. Here's another cofactor alloy, the only one we really know about. It's found by Eckhart Quant's group in Kiel. It's a titanium, nickel, copper, cobalt. It's also super interesting, and it also has this tremendous compositional sensitivity, as everything in this does. So here's titanium, nickel, copper, cobalt. Here's titanium, nickel, copper, cobalt. Now look at the subscripts. 50.8, 54.7, not so close, but pretty close. 34.2, 30.7, 12.5, 12.3, 2.5, 2.3. It's really pretty close, this alloy to this alloy. But the behavior, this alloy satisfies the cofactor conditions. This alloy doesn't. This alloy is the usual garbage, you know. There's the first hysteresis loop. So by cycle 10, it's a very different loop. There's a lot of plastic deformation. The loop is completely changed by cycle 200. By cycle 200 here, it sits right on top of the original curve. This is stress-induced phase transformation, I guess, I guess you could guess that. And it's complete transformation each cycle. But the really amazing thing is, and this is intention, is this is cycle 1, the black curve, and that's cycle 10 million, the red curve. So that's really amazing reversibility of a phase transformation under tension. It's done in a thick film. It's very carefully, the surface is electropolished. All the details are, this group in Kiel pays attention to all the details, but still it's really a spectacular result. So we hope that phase transformations can become generally reversible, and that would open up many applications of these materials. I want to talk about one of those, in my mind, all the real exciting things with these transforming materials involves other properties, and I'll talk about magnetism as one of those properties. So I want to talk about nickel, manganese, indium, tin, and antimony. And they're magnetic materials, but they also undergo phase transformation. So for example, this nickel, manganese, indium alloy has a magnetic ordering at this temperature. This is magnetization versus temperature. And then it undergoes a phase transformation here. So you could actually you could represent it in this case with a vertical temperature axis. Here's the austenite phase, the cubic phase, and it magnetically orders, forms magnetic domains, you might say, and then it transforms, and this is also magnetically ordered. So that's an interesting case. In this case right here, this alloy is even more interesting because the high temperature phase is non-magnetic, and you jump by phase transformation to a magnetic phase. These are interesting cases, but the real thing that caught our eye is this work of Kainuma in his group. And he took one of these alloys, of these type, nickel, cobalt, manganese, tin alloy, certain composition, and he showed that if you put a very strong field, that's 7 Tesla, so that's a huge, huge field. You'd never be able to use that field in a device, but nevertheless, he got a magnetization of 100 EMU per gram. You know, if you don't know these units, that's a big, strong magnet, okay? If you take off that huge field, it goes away. So in fact, that's the diagram for this alloy. The austenite is non-magnetic, and the martensite is non-magnetic. But now you have to think, make a phase diagram in your mind. There's temperature, composition. But now you have to put a third axis, which is magnetic field. And what he's doing is over here on that third axis with some huge strong field, he's getting a phase that you can't get without that. It's not on the ordinary zero magnetic field phase diagram. But if you understand a little about phase diagrams, you can realize, well, if I can do it with magnetic field, I can also do it by changing composition. So I could try to stabilize with composition this particular phase with this enormous magnetization. So we did that, and we were also trying to make lambda 2 equals 1, as you can imagine, and this is the alloy we got. It's maybe not the final story about this alloy system, but it had about 6 degrees hysteresis with that lambda 2. We could certainly do better, but that's the neat thing about this is that this is the phase transformation. The austenite phase has really a huge magnetization. So this is with a very small applied field. So that's the stable phase. So this goes from a non-magnetic material to a very strong magnet. This is about the same strength as iron at that temperature. So that's quite interesting. You have a material, once on the table, it's non-magnetic. You go through a phase transformation. Maybe you could even go through a phase transformation with 1 or 2 degrees hysteresis. You end up with a very strong magnet. You cool it down again, and it's non-magnetic. Okay. It has very interesting magnetic behavior and so forth. It's getting a bit late, so I'm not going to go into all the details. But just so you can see a little cartoon of this, how this behaves. I think maybe Yin Tao Song did this demonstration. Did you catch that? So that's a little copper finger there that's heated right there. And this is a permanent magnet. So when it goes through the phase transformation, of course, it gets magnetized. And then it follows the field lines over to this really quite far away permanent magnet. It's not such a strong magnet either. So that's quite an interesting material. In fact, if you think about that, this is an energy conversion demonstration. And we made this a bit more sophisticated. So this is something you can use transforming materials for, and it's probably one of the more interesting things you can do. Is in this case, in the case of this magnetic material, you take this piece of this nickel, cobalt, manganese, tin, you put it on top of a permanent magnet so that it biases it. You notice that if you look at these magnetization curves, even at half a Tesla or even at 0.05 Tesla, you get a large change in magnetization. So, but you need to bias it. If you didn't bias it with an applied field, it would just demagnetize itself. It's a soft magnet. Okay, go back to this. So you bias it with and now you heat it up just a few degrees through the phase transformation, especially if it has low hysteresis. And these are the 2 Maxwell's equations you should think about. So when you heat it up, it goes through the phase transformation, and it gets a big dm dt. So by this dipolar relation, dm dt is partitioned between dB dt and dH dt. okay? But you want the big dMdt to go all into dBdt. That's governed by so-called micromagnetics. And it has to do with the shape of this and other factors. And so the main thing is the shape, actually, the shape effect. So you make a good shape so that big dMdt gives you big dBdt, and then dBdt is curl E. That means you drive a current in the coil. So there's an energy conversion device. You heat it without an electrical generator. It generates a current in a coil. Okay? And that's not the only way you can do this. There's many ways with phase transformations you can convert heat to electricity directly without an electrical generator. And there's a little ordinary differential equation which can be got from these two equations plus cylindrical symmetry and so forth, and you can make a little model, and you can compare with theory with experiment, and you can really understand how this works both from the point of view of the phase transformation, the material, and the electrodynamics. I won't belabor this because it's a bit getting late, but I will mention that, and there's a nice interesting story that goes with this from the thermodynamic and the electrodynamic viewpoint. But I will mention that Manfred Kohl's group in Karlsruhe, they've been working, they took this up beyond where the work we did, and they've done arrays of cantilevers using these materials, and they recently demonstrated power densities that exceed thermoelectrics. So that's, of course, a big milestone in this kind of energy conversion from small temperature differences. So I don't think, in fact, in the end, I don't think that magnetism is the best way to do this, but anyway, that's another story to be told in the future. But, you know, there are lots of sources of temperature differences on Earth and maybe even in Hong Kong at small temperature difference. And, of course, what comes to mind immediately is these solar thermal plants, and this is in fact Nick Shriver's. He's the guy that took the TEM picture, or his student Remy did that, and there's me. And if you could look at my knuckles there, you would see that they're completely white because we're sitting right there, and this is hugely far off the ground. This is, and I'm afraid of heights. So, so this tower is enormous. And there's a big, huge black tank of water up here. And they're doing energy conversion by focusing the rays of the sun on this black tank. And there's some cold water down here somewhere that you don't see, which is an important aspect. And they're doing solar thermal energy conversion by what? By the 17th century method, essentially. Okay? It's steam generation. But why do you have to do all that? Why can't you just have... Why can't you focus the rays of the sun on a material which creates a small temperature difference and directly convert heat to electricity? I don't see why not. So, I mean, there should be other ways to think about this, and it's definitely worth investigation. There's also other sources on Earth which are, you know, quite steady temperature differences, 5, 10, 20 degrees C, which is ideal for these kind of transforming materials. So that's the end of my talk. Thank you very much.
Recently, there are some materials called high entropy alloys.
Yes.
I'm wondering if this kind of transformation.
Okay. So first of all, I have strong opinion about high entropy alloys because the name is hugely misleading. The entropy that they calculate has nothing to do with the entropy in this material, because of the fact that and this is something, it's actually closely related to my diagram of the wiggly energy and the molecular dynamics, is in order for when you calculate the entropy of the material, you count the number of states, essentially. The simplest model is you count the number of states. But the material actually has to visit those states in order for it to be meaningful as the entropy. Otherwise, it's a constrained material. Those high entropy alloys don't visit all those states that are by switching those atoms. The atoms are just vibrating about their equilibrium position. So it has nothing to do with the entropy in this material. But anyway, so it's just a name. But of course, they're very interesting alloys because of the fact that they, you know, have these very different elements distributed in lattice in many different ways and so forth. And, they would not be materials that would immediately come to mind for phase transformations. But as far as I know, they haven't been investigated. You can have phase transformations in disordered materials. In fact, all the alloys I showed you are to some extent non-ordered. They have sublattices on which the elements are like, titanium, nickel, palladium. The nickel and the palladium are substituting on a sublattice in some kind of random way. So there's no reason, if there's some kind of skeletal sublattice, that you couldn't have phase transformations in those. But I don't know any interesting property which would come from that. Yeah.
Thank you very much for your very, very inspiring, stimulating lectures. Thank you. I have two questions.
Yeah.
The first question is the cofactor or lambda 2 equal to 1 condition derived on the lattice
yes.
free of stress.
Yeah.
They perfectly satisfy this lambda 2 cofactor.
Right.
My question that people asked many times under externally stress-induced.
Yeah, that's right. And even, of course, it's...
my question is because in that case is most often the hysteresis are not very small here, about 100 or... But the reason could be under the externally applied field, or whether stress field or magnetic field. This originally stress-free perfect cofactor condition or lambda 2 equal to 1 condition may be violated because the stress could have different magnitude, different directions.
Right.
Is that a reason for this close to cofactor or lambda 2 equal 1 materials? Their hysteresis on the stress still how to say not vanishing?
Yeah.
This is
okay. So
what is the reason? How the stress?
Okay, that's a very good question. So first of all, this alloy, for example, as you say, the hysteresis is not that small. The zinc gold copper alloy had quite small hysteresis. The beta 1 to beta 1 prime transformation in copper aluminum nickel has very small hysteresis. It has lambda 2 very close to 1. So there's different cases, and we don't really understand. But so first of all, so this alloy satisfies cofactor conditions under 0 stress, but it seems to be playing an important role on its reversibility under stress. Okay, so part of that can be that the stress does not change the lattice parameters that much. So if you satisfy cofactor conditions under 0 stress, you could approximately be satisfying them under stress. But of course, as soon as you stress something, cubic is no longer cubic. Tetragonal, or in this case, orthorhombic, is no longer orthorhombic. Everything is triclinic. Everything is inhomogeneous. So it's quite. But nevertheless, the strains are small perturbations of strains, which would be. So that could be relevant. But the differences we don't understand. Another thing I can say is which was an experiment done by Eckhart Quant's group, is he measured, along this loop, he measured lattice parameters. Okay, now, of course, as I say, at this point in the loop, or at this point, or any point on this loop, the cubic is no longer cubic, the orthorhombic is no longer orthorhombic. But if you take an alloy which is stressed to this point, and you stick it in the X-ray machine, the peaks that were orthorhombic when you started are sort of orthorhombic. Not only sort of, they broaden a little bit and they shift a little bit, okay? So it's quasi-orthorhombic somehow, and it's somehow quasi-cubic. Again, I'm saying something about the perturbations. When he does that, he finds that when he's on this loop, it's even more closely satisfying the cofactor conditions than under 0 stress. So this happens to be a case in which you somehow, if you ignore somehow that nothing is cubic anymore and everything's triclinic, if you ignore that, just take the peaks from the X-ray machine, index it as orthorhombic, index it as cubic, calculate the cofactors, you'll find that they're even more closely satisfied here than they are here. what does all this mean? I don't really know. You know, there's some observations we have. I think the thing that you really the point you're mostly raised, and we really have no answer, is this is a fairly big hysteresis. Even though it's highly reversible, this is a fairly big hysteresis. I mean, this one is a quite small hysteresis, and so we just have we don't really understand that. Of course, there's many other factors that can be playing into this, like grain size and precipitation and so forth, and that all that needs to be understood. But I would say, you know, on the positive side with this, I would say that this is somehow the main effect, you know, is getting this compatibility right is probably the main thing, and then one can do even better, you know, with these other factors. That's my belief, but yeah.
Thank you, because sometimes the strain on the external stress could be very high, like 1%, 2%, even before phase transition. Yeah. For example, nanostructure materials are very high stress.
That's right.
They're over 1,000 megapascal.
Yeah.
The elastic strain already 1 or 2%. Okay.
Yeah.
My second.
So that's actually.
Thank you.
Yeah.
Thank you for your explanations. The second question maybe go beyond a little bit, but we know that the composition can change the fundamental length scale of lattice constant ABC, for example, right?
Yeah, we use that.
You use that
with precipitation.
But go further from more fundamental physics, chemistry point of view. Mm-hmm. How this composition change the ABC?
Oh,
maybe your research maybe could be open a new area.
Well,
now it's called material informatics or science of phase diagram. Material informatics to understand how composition changes.
I think you're right.
It's kind of like searching, right? It's like cooking.
Yeah, that's right. We need to make that more systematic.
But now I think, what is the situation? Can you give a
I think it's you have a great idea, and I mean it needs to be developed. This mapping between composition and lattice parameters, that's obviously needs to be improved and predictive. The only remark I'll make is something that's very puzzling to us. Is we take there's now quite a number of these kind of alloys. Not all, and this one satisfies the cofactor conditions, but there's other nickel titanium copper or nickel titanium copper cobalt alloys that satisfy lambda 2 = 1, but not the full cofactor conditions. Okay, so you plot. Okay, so you plot this in this weird way. You plot the other two eigenvalues. You take all alloys you know that have lambda 2 = 1 and are cubic to orthorhombic, which is a lot of them, including the nickel titanium palladium alloy I showed. You plot them on the lambda 1, lambda 3 plane because you're assuming lambda 2 is 1, and these alloys all satisfy lambda. They fall in a perfect straight line in this plane. That's some fundamental physics that I have no idea why those alloys should fall on that line. And if you follow that line to another line, which is the locus of points at which the cofactor conditions are satisfied, you get exactly that alloy. So Eckhard Quandt stumbled on exactly the intersection of some physical thing, and I think it can be discovered by some informatics approach you're suggesting. So there are some kind of weird accidents that we've noticed that would be very, very interesting to elucidate by those approaches. Yeah.
Yes, please.
So I guess from your definition, the phase transition of water from liquid to steam is highly reversible. It's always at the same time.
Yeah, that's right.
So can I flip the question and ask, why is water so reversible?
I mean, so water doesn't have any of this energy barriers that come from stress.
But you have nucleation energy.
Yeah, there's interfacial energy, which is quite big in water, and you know, we used to do this experiment in my lab where you take where you put in the DSC machine, do calorimetry with a droplet of water, okay, and you choose ordinary water. And this is, I'm going to describe the freezing transition rather than the other one, but still it's kind of relates to your question, is you put this droplet of water in the DSC machine and you lower the temperature till it freezes. If the drop of water comes from the tap, it freezes at 0 always. If the drop of water comes from the deionized water in our mechanical engineering department, which is not that clean or anything, but it's labeled deionized water. Okay, the drop comes from there. You put it in the DSC machine. It consistently melts at minus 11 C. So there are these things that I would say that a lot of so if I could make a prejudiced but blanket statement, I would say a lot of these phenomena. The hysteresis of phase transformation is energy barriers set up by interfacial energy or by elasticity or by other phenomena. Maybe also magnetic domains could be playing a role. And I tend to view these things all as energy barriers. And when so in fact, in the martensite case, you imagine a nucleus of martensite. I'm getting away from your water issue, but you imagine a nucleus of martensite and the plate of martensite's widening, and you can see as it widens, or you can calculate that there's an energy barrier as a function of its width, which involves a competition between this elastic and interfacial energy. And you can see that there's this quite big energy barrier, and if you plot the same barrier if you plot the same thing using the same material parameters but make lambda 2 equals 1, this barrier almost disappears. So there's a huge sensitivity to lambda 2 equals 1. But in something like water, there might be huge sensitivity to, whether there's a tiny amount of detergent in the water or whether it's deionized or not. And I think it's all about energy barriers, yeah. That's blanket prejudice statement, but
maybe another comment before next questions, because water gas, liquid gas phase transition not only reversible, but also there's no reliability issues. But the solid cycle they will fracture because the stress
is obviously not
because of the stress.
See, that's why we want to do this so much in solid-solid phase transformations, because we have these properties, hard material properties like magnetism for electricity. We have in VO2 4 order of magnitude change in electrical conductivity. We have all these interesting functional properties that we can try to have a big change of at the transformation. But then we have these reliability issues, and this is an attempt to try to solve those issues, make them reversible.
Yes, my question is actually much simpler than the conversation going on. In terms of application, what sort of application would this material be used in, and is there any relation to biomedical?
Okay, so as I said before, I come from Minneapolis, and we have all those biomedical device companies in Minneapolis. It's a very prominent part of our industry there. And the biggest company of all is Medtronic. If you go into Medtronic and the front door, and in fact they have a little museum there of all their medical devices. There are rows of medical devices. Probably a quarter of those devices have nickel titanium shaped memory materials in them. So it plays a huge role and they use it mostly for its elastic properties. And so the stent, of course the stents originally were stainless steel, and then they found nickel titanium because of its elastic properties. Basically, the large elasticity you get in this curve is important for a stent which receives a lot of deformation, like in peripheral stents. But now these days they're doing more and more heart stents with nickel titanium. So it's the basis of a huge industry. It's a $5 billion industry as nickel titanium medical devices. It's projected to be $20 billion industry by 2019. It's really big. But, we who work in the field, we love the functional properties. So we think that the future is really integrating this with magnetism, ferroelectricity, conductivity, maybe superconductivity, those kind of having phase transformations involving changes of these properties. And we could see there should be, one should think very creatively about applications of this new materials. But the truth is that they really made a big impact and continue to make a growing impact in the medical devices, in stents and guide wires, dental arch wires. They even have now, there's brain stents, so there's a family of stents being developed now that can remove clots in the brain and use this kind of effect. So there's a whole families of these medical devices that make use of exactly that effect. But I think the future is the more functional properties. Yeah. Also, optical materials is also a very interesting phase transformations, which an abrupt change of an optical property that's interesting, and you can turn on and off, or even you can induce the phase transformation with light. That's a very interesting area in polymeric phase transforming materials, pneumatic elastomer materials, which again are closely somehow related to these. So lots of stuff on the application side that's, I would say, very promising. And there's also, as I said, a very successful and quite recent industry based on phase transformations. Yeah.
So, Richard, my background in mathematics is not good enough, so I'm just reading your statements and conclusions later, so I'm going to ask my question later too.
Yeah, sure.
You said, as long as you satisfy the compatibility, the middle eigenvalue equal to 1, you can always have your reversible phase transition or transformation regardless of the volume change. But is there an upper limit for how much volume change you can take up? Like, even if there's no thermodynamic limits, I would expect there's a kinetic limit because there's volume change. You need to displace the material at a certain rate, and that rate cannot be infinitely fast.
Yes, that's right. I mean, so first of all, let's just take lambda 2 equals 1. That's the simplest condition. Forget about the cofactor conditions because that's more involved. But just lambda 2 equals 1, which is a perfect interface between the two phases. That's compatible with arbitrarily large volume change because of the fact that the material can undergo the volume change perpendicular to the interface, But of course, as the volume change gets bigger and bigger, that kind of transformation strain gets more and more anisotropic and more kind of unrealistic. It'd be extremely hard to find a material which had such a change. Now, whether you would lose these good properties with large enough volume change, but still having lambda 2 equals 1, I don't know. You may well be right that would, But even when there's no volume change, these materials, they undergo large shear, and so there's still all the things you said about kinetics and so forth. You can make the same argument for the large shear too. So and of course there are kinetic effects in these materials, and so and I didn't talk about them. In fact. So there's aging effects, effects that come from the fact that at finite temperature, atoms can actually switch position, especially under stress, and there can be compositional, it can drive diffusion or local changes in local ordering is a very typical aging effect that can happen in these materials. So that's there. I would say this is the more important thing, but that's definitely there. And what you say about the volume change, could well be true if it's large enough, but it becomes more and more difficult to find such an anisotropic transformation strain that has large volume change. But I mean, as you work on these interesting battery materials, it's definitely something to think about in those cases where, that you could try to somehow make lambda 2 equals 1 in some kind of battery material, and it may well be effective, or make lambda 2 closer to 1 or something like that. Yeah, seek transformation strains due to lithiation, which are highly anisotropic, for example. Yeah.
So, as shown in this slides, we see that lambda 2 value is closely to the barrier height of the phase transformation. So, how about the value of the cofactor conditions, like any
that's a very good question.
Quantitative relation relate the value of the cofactor condition to the landscape of the free energy, so that we can understand the phase transformation more precisely or quantitatively. How to link it.
There's only one thing we have, and it's not very, it doesn't really answer your question, but there's one thing we have is under stress, we've looked at what happens if you turn on and off the cofactor conditions. Okay, and we're thinking of a polycrystal, and so an arbitrarily oriented grain, and we look at the strain in the direction of the stress for an arbitrarily oriented grain. Another way to think of it is instead of an arbitrarily oriented grain, fix the orientation of the grain and let the tensile axis move around. Okay, so then you can think of just a vector, and there are certain directions in which the crystal cannot deform very much in that direction. If you did a polar plot in 3 dimensions of the strain in direction E, and that's direction E, and you plot the length of the vector as direction E, you get a kind of bumpy sphere. Okay, and there's certain points where there's little umbilical points. In other words, in those directions, you can hardly deform the crystal at all. Okay, if it does not satisfy cofactor conditions. Now you turn on the cofactor conditions, and it interpolates those spots. So it somehow tells you it improves the deformations possible in badly oriented grains. That's what which can be a very important thing. That's the only thing quantitative I think I know. I can tell you quantitatively something about that, but yeah.
Okay, let's thank Professor James again.